All right, let's talk about something that's absolutely critical for any serious Python developer, object-oriented programming. If you think of yourself as a software architect, well, this is your guide to building code that's strong, clean, and professional. Okay, let's get into it.
So first off, why should you even care about this? I mean, really care. Well, if you're aiming to land a Python job, listen up, because this isn't just some nice-to-have skill. It's an absolute must-have.
The reality is, if you look under the hood of almost any professional Python project, we're talking web apps, APIs, big backend systems, you're going to find OOP at its heart. Mastering this stuff isn't just for a test. It's the key to actually building real software and, you guessed it, landing that job.
So let's start by laying down the foundation. The entire massive concept of OOP really just boils down to one simple but really powerful idea: the difference between a blueprint and the actual thing you build from it. A class, that's your blueprint. It doesn't actually do anything on its own. It's just the design, right? It's the template, the set of instructions for what you're planning to create. It defines all the properties and the behaviors that anything made from it is supposed to have.
An object, on the other hand, well, that's the real deal. It's the car that actually rolls off the assembly line, the house that gets built from the plans. It's a real, living instance of a class that you can actually use and mess with in your code. So how does that blueprint, the class, actually turn into a real object? Well, that's where the constructor comes in. In Python, this is a special method called _init. The moment you create a new object, this thing runs automatically. It's like the factory foreman that takes the initial details, like Toyota and 2022, and uses them to build and set up that brand new object just for you.
Okay, so our foundation is solid. Now, let's build on top of it with the 4 pillars of object-oriented programming. You're going to want to pay close attention here because I can almost guarantee you these concepts are going to come up in any technical interview you have. These are the fundamental rules of good software design. First up, we've got encapsulation. The main idea here is pretty simple. You bundle the data and the methods that operate on that data all together in one neat package, and then you protect it from the outside world. It's just like a capsule. All the important stuff is sealed safely inside. And this example shows you exactly why that's so important. Think of your bank account balance. You don't want any random part of the code to be able to just reach in and change that number, right? No way. So you lock it away. To interact with it, you have to go through official methods like deposit or get_balance. This keeps your data safe and your code predictable. Next up, pillar number 2, inheritance. This is all about not repeating yourself. It lets you create a new child class that automatically gets all the features and methods from an existing parent class. You write the code once in the parent, and all the children get to use it. Just look at this. The animal class has a speak method. Because our dog class inherits from animal, it just gets that method. We never had to write a speak method inside the dog class itself, but our dog object can still use it. It gets that power for free, which is just incredibly efficient. Pillar number 3 is polymorphism. It's a fancy word that just means many forms. The idea is that you can have one single name or one interface that can mean different things depending on the context. In our code, it means we can call the exact same method on different objects, and each one will respond in its own special way.
And this is the classic example. You have a cat and a dog, and they both have a speak method. When we just tell an animal to speak, Python is smart enough to figure it out. If the animal is a cat, it meows. If it's a dog, it woofs. It's the same method call, but we get completely different behavior. That's polymorphism.
And our final pillar is abstraction. This one is all about hiding all the messy, complex details on the inside and only showing the simple, essential features on the outside. It's like creating a contract that other classes have to follow. So here, our shape class is abstract. You can't actually make a shape object. It's more of a rule book. It says, hey, any class that wants to call itself a shape must provide its own area method. This forces the square class to follow the rule, which keeps all our shapes consistent and reliable. Okay, so you've got the 4 pillars down. Now, it's time to level up. Let's get into the professionals toolkit. These are the concepts that really separate the beginners from the seasoned software architects. So this is a really crucial difference to understand. A class variable, like species, belongs to the blueprint itself. That means it's shared by every single object you create from that class. But an instance variable, like self.name, is totally unique to each specific object. So every dog is a canine, but each dog has its own name. Now, this is a huge one in modern software design: composition. Instead of an is-a relationship, like we saw with inheritance, a dog is an animal, composition gives us a has-a relationship. You build your big, complex objects by basically putting other smaller objects inside of them.
The perfect example is a car. A car has an engine. It wouldn't really make sense for a car to be an engine, right? So instead, when we build our car object, we also create an engine object, and we just put it inside. This has-a approach is super flexible, and you see it everywhere in big professional systems.
And finally, let's talk about the @ property pattern. This is how pros manage access to an object's data. It's a 3-step dance. First, you make an attribute private. Second, you create a getter that lets other code read it. And third, you create a setter that acts like a security guard. It lets you add logic to check any new value before it's actually assigned, which is amazing for preventing bugs.
Wow, okay, we have covered a lot of ground. We've gone from the basic blueprint all the way to professional design patterns. So now it's time for the final inspection. What do you absolutely have to know to nail that job interview?
This is it. This is your checklist. If you can confidently explain every single item on this list, the 4 pillars, why you'd use composition, how a property decorator works, the difference between a class method and a static method, you are going to be in an amazing position. You'll prove that you really understand professional Python. Look, theory is great, but practice is where the magic happens. The single best thing you can do to make all of this stuff stick is to just build something. It doesn't have to be huge. A simple banking system, a little shopping cart, that's the perfect way to make these concepts really click into place. So we've walked through the architect's guide. You have the blueprints now. You have the patterns for building robust, professional, amazing Python applications. The only question left is, what are you going to build? Hey there, and welcome. Ever find yourself wanting to make your Python code cleaner, more organized, and, well, more like the real world? Then you're in exactly the right place. Today, we're going to pull back the curtain on object-oriented programming, breaking down classes and objects into ideas you can actually use. So let's kick things off with a simple question. I mean, really think about it. A car isn't just one thing. It's got a make, a model, a year, and on top of that, it has actions, right? It can drive, it can stop, it can honk. How in the world do you bundle all of that together in a way that makes sense? That puzzle right there, that's exactly what we're about to solve.
All right, so to crack this, we gotta shift how we think a little. We're moving away from just writing a long list of commands for the computer to follow. Instead, we're gonna start creating these little objects in our code that act like models of real-world things. It's less about giving orders and more about building a system.
And this leads us to probably the single most important idea for today. It's a simple analogy, but it's everything. Just think about the difference between a blueprint for a house and the actual house you get from it. Okay, so here's the key takeaway. The class is the blueprint. It's the master plan. It lays out the rules, saying every single car we make is going to have a make, a model, and a year. The object, on the other hand, is the actual building. It's your 2020 Toyota Camry, built from that plan. It's the real deal with actual values. Let's dive into some code and get our hands dirty. This here is about as simple as it gets. We're just telling Python, hey, heads up, I'm creating a new concept, a new blueprint, and I'm calling it a car. And that pass keyword, it's just a placeholder. It basically says, yep, this is a thing, but we'll fill in the details later. An empty blueprint isn't much use, so we need to add the assembly instructions. And that's where this special underscore init method comes in. Think of it as the constructor. It runs automatically every time you create a new car object. It takes in the details, the make, model, and year, and that self keyword is just a way of saying, hey, attach these properties to the specific car we're building right now. And this is where the magic happens. We use that one single car blueprint to create car 1, a Toyota Camry. Then we use the exact same blueprint again to create car 2, a totally separate and unique Honda Civic. See that? One plan, endless, unique creations. Okay, so our cars are no longer just concepts. They exist, they have data, but what can they actually do? A real car does more than just sit there. This is where attributes and methods come into play. So the data, the make, model, and year, those are its attributes. They're the things an object has. And the actions, those are methods. They're pretty much just functions that are attached to the class. Here, we've given our car a description method. It's a behavior that lets the car describe itself using its own attributes. Okay, check this out. When we call that method on car 1, it uses its own data to tell us it's a 2020 Toyota Camry. But if we were to do the same thing for car 2, it would use its data to say it's a 2021 Honda Civic. It's the same action, description, but the outcome is totally unique to each object. Now that is incredibly powerful. Now there's a quick but really important distinction we need to make. The attributes we've seen so far, like make, are instance attributes. They're unique to each car. But what about things that are true for all cars, like, say, having 4 wheels? We can define that as a class attribute. And now every single car object we stamp out from this blueprint will automatically get it. All right, we've got the basics down. Blueprints, buildings. Now let's level up and talk about the 3 superpowers of object-oriented programming. This is the stuff that really makes it a game changer for writing big, complex programs. First up, encapsulation. Sounds fancy, I know, but the idea is dead simple. Keep your data safe. It's all about bundling an object's data together with the methods that are allowed to work on that data. It's like putting it all inside a protective capsule, hiding the messy details from the outside world. Think about a bank account. You definitely don't want some random piece of code to just reach in and change your balance, right? No way. With encapsulation, we make the balance private. The only approved way to change it is by going through a method we created, like deposit. This is huge for preventing weird bugs and keeping your data trustworthy. Superpower number 2, inheritance. I mean, why reinvent the wheel? Why build a whole new blueprint from scratch if you can just borrow from one that already exists and then add your own custom features? That's what inheritance is all about. For example, it's pretty clear that a dog and a cat are both types of animal, so they can inherit common stuff, like a name, from a parent animal blueprint. We're not repeating ourselves. That's super efficient. But then each one can have its own special speak method. The dog barks, the cat meows. It's all about reusing what you can and specializing where you need to. And our final superpower, polymorphism. It's a bit of a mouthful, but it comes from Greek and just means many forms. And the core idea is this. You can have a bunch of different objects, and you can ask them all to do the same thing, and they'll each do it their own way. Just look at this piece of code. We have a list with a dog and a cat in it. We can just loop through and tell each animal to speak. We don't have to check if it's a dog or a cat. Python is smart enough to figure it out and call the right version of the speak method for each one. This makes our code unbelievably flexible and clean.
All right, deep breath. We've gone through blueprints, objects, and the 3 big superpowers. Now, let's tie it all together in one final master build to see how it all works in practice.
So let's say we're modeling a company. We're going to start with a base blueprint, the employee. Makes sense. Every employee has a name and a salary. And right off the bat, notice what we're doing with that double underscore in front of salary. That's encapsulation in action. We're protecting that sensitive data from day one. Okay, but not all employees are the same, right? So let's make a more specialized blueprint for a manager. A manager is an employee, so this is a perfect job for inheritance. That super.super.init line is just telling Python, hey, go run the setup from the parent employee class first to get the name and salary. Then we add the new unique thing for managers, the team size. So there you have it. Let's do a super quick recap. Think of this as your personal checklist for getting started with OOP. You start with class to make your blueprint. You use __init to set up its properties. You add methods for its actions. You create actual objects from that class. And then you really level up by using inheritance and polymorphism to make your code powerful, flexible, and so much easier to manage. And just like that, we've gone from a simple problem to a really powerful way of thinking about and structuring your code. You now have the fundamental tools, the blueprints for building your own complex, elegant, and maintainable software. You've got the blueprints now. The real question is, what are you going to build?
So, you want to level up your Python skills, right? Go from just writing scripts to building real, professional software? Well, to do that, you absolutely have to master object-oriented programming. And sitting right at the heart of it all is one crucial concept: inheritance. In this explainer, we're going to break down exactly what it is, how you use it, and why getting this right is your ticket to acing that next technical interview.
Okay, so let's kick things off with a big question. I want you to think about these massive code bases, the kind of stuff that powers big tech companies or complex back-end systems. How on earth do professional developers manage all that complexity without just copying and pasting code everywhere?
Well, the secret weapon they all use is a fundamental principle of object-oriented programming, and it's called inheritance. This is the magic that lets them write code that's clean, that can grow and change easily, and that's super efficient, and we're about to dive right in. Now, inheritance isn't just some abstract academic thing. No way. It actually gives your code some serious superpowers. You get to reuse code you've already written, which means less typing and fewer bugs. It lets you add new features without breaking your old code, and it helps you build a really clean, logical system that follows the #1 rule of good programming: don't repeat yourself.
All right, so what is this inheritance thing really? Let's strip away all the jargon and get right into the core idea, and I promise it's simpler than you think. The easiest way to think about this is, well, it's just like real life. A child class can inherit traits, or in our case, properties and behaviors, from a parent class. This means the child class just automatically gets all the parent's functionality for free without you having to rewrite a single thing. Okay, check this out. It's a super simple but perfect example. Let's say we have a general animal class, and all animals need to eat, right? So we give it an eat method. Now, when we create a more specific dog class, we can just say it inherits from animal. And boom, the dog class now knows how to eat. You don't have to write that logic again. That is code reuse in action. Okay, now we're getting to the part where honestly a lot of beginners get stuck, but we're going to make it super clear. How do we actually make that connection between the child and the parent work properly? The key is a handy little function called super. So here's the trap. This is the thing that catches everybody at first. Let's say your parent class has its own little setup routine, that special __init__ method. You might think the child class would just run that automatically, but it doesn't. And that can cause some really strange bugs if you're not paying attention. This slide shows it all, the before and after. On the left, you've got the problem. The child's init is totally ignoring the parent's setup. The connection is broken. But on the right, bam, we fix it with one simple magical line. Super.init.init. That one line creates the bridge and tells the child, hey, before you do your own thing, make sure you run our parent's setup first. So, if you remember one thing about this, remember this. Super is that essential bridge. It's the official handshake between the child and the parent. It guarantees everything gets set up correctly, all the way from the top of the family tree down to the bottom. But here's the cool part. Inheritance isn't just about blindly copying everything. A child class can look at a method it got from its parent and say, you know what, I have a better, more specific way to do that. A generic animal might just make a generic sound. But a dog goes woof. That's called method overriding. It's all about specialization. Okay, so we've got children inheriting from parents, and they can even change things up a bit. This leads to all sorts of different family structures, right? Let's take a quick look at the different patterns you're going to see out there in real code. First up, the most common, the one you're going to use 90% of the time, is single inheritance. It's exactly what it sounds like. One parent, one child. Our animal class having a dog child is a perfect example. It's simple, it's clean, and it's incredibly useful. But what if we want to go deeper? You can. That's multi-level inheritance. It's like a family tree going down the generations. You could have a poodle that inherits from a dog, which in turn inherits from an animal. Each level gets more and more specific. Then you've got the opposite situation. This is hierarchical inheritance. Think of it like one parent having a bunch of different kids. That same animal class could be the parent to a dog, a cat, and a fish. They all share the basic animal stuff, but each one goes off and does its own specialized thing. And now, for the one that makes Python, well, really special, and sometimes a little tricky. We're talking about multiple inheritance. A single child class can actually inherit from 2 or even more parent classes at the exact same time. It's super powerful, but it also raises a very important question.
And that question brings us to a really, really important topic. Understanding this, the method resolution order is what truly separates the beginners from the pros. Seriously, this is the stuff that interviewers love to ask about to see if you really know your stuff.
So let's set the scene. You have one child class, but it has two parents. And what if both parents have a method with the exact same name? Uh-oh, when you call that method on the child, which one gets used? Who wins the tie?
This classic headache is known as the diamond problem. But don't worry, Python isn't just going to guess. It has a super clear, predictable rulebook for this exact situation. It's called the Method Resolution Order, or MRO for short. Think of it as a search path that Python follows every single time.
So how does Python figure this out? It follows that MRO path, and it's always the same. Let's trace it together. First, Python looks in the child class itself, D. If the method isn't there, it moves to the first parent you listed, which is B. Still no luck? It then checks the second parent, C. Only after it's checked all the direct parents does it move up to the grandparent, A, and then finally to the base object class that everything in Python inherits from. It's a clear, predictable order, so there's never any confusion.
All right, that was a lot of theory. But theory is useless if we can't apply it, right? So let's look at how all these ideas come together in a practical example, something you might actually build in a real job.
Okay, check out this payment system. This is a super common pattern you'd see in a real back-end job. You'd start with a base payment class. It handles all the common stuff, like the amount and the transaction ID. Then you create specialized child classes, like credit card payment and PayPal payment. They both inherit that common logic, but each one overrides the main process method to handle its own specific details. It's a perfect, clean, and easy-to-extend design.
And look, I really want to drive this point home for your career. This quote right here says it all. You can't just memorize the syntax for class and super. That's not enough. You have to understand the why. Why does it work this way? How does Python solve problems like the diamond problem with MRO? That deeper understanding is exactly what interviewers are looking for.
So there you have it. We've gone from the basic idea all the way to the pro-level stuff that trips people up in interviews. You now have the knowledge to not just use inheritance, but to truly understand it. So the only question left is, are you ready to get out there and start writing some cleaner, more powerful, and way more professional Python code?
All right, let's get right into it. Today we're talking about polymorphism. And believe me, this is one of those big, powerful ideas in Python. If you're looking to write code that's not just functional, but clean, professional, and easy to scale, then this is something you've absolutely got to get your head around. But first, let me ask you something. Have you ever just stopped and thought about the len function? I mean, we use it all the time, right? On strings, on lists, on dictionaries, and it just works. How does that one little function know how to handle all these completely different kinds of data? Well, it's not magic, and the answer is exactly what we're talking about today.
So, that magic we were just talking about, it actually has a name, polymorphism. It literally means many forms. And in this explainer, we're going to pull back the curtain and see exactly how it works and why it is so important for writing really elegant code.
You know, to really get why polymorphism is such a game changer, you have to see what life is like without it. On the left, you've got this absolute tangled mass of if-else statements. Your code is constantly playing 20 questions. Are you a string? Are you a list? It's rigid, it breaks easily, and it's a total nightmare to update. But then you look on the right. With polymorphism, it's just one single clean action. The code becomes flexible, and suddenly adding new things is a breeze.
So what is it really? Here it is, the big definition. Polymorphism is all about one interface, many forms. It's this beautiful idea that we can ask different objects to do the same thing by calling the same method, and each object will just know how to do it in its own special way. This right here, this is the aha moment.
Look, if there's just one thing you take away from all this, let it be this simple, powerful idea right here. The whole entire concept boils down to these two lines. Same method name, different behavior. That is the beating heart of polymorphism. Okay, so we know the what and the why, but what about the how? How does Python actually pull this off? Well, let's unpack the most common ways you'll see this in action, starting with the classic approach that's common in a lot of object-oriented languages. So, this classic approach usually starts with something called inheritance. Let's imagine we have a very general or parent class. We'll call it animal. And this animal class has a method called speak. But you'll notice it's super generic. All it does is say, the animal makes a sound. Pretty boring, right? Now, we create what are called child classes, like dog and cat, and they both inherit from our general animal. But here's the crucial part. Each one provides its own, much more specific version of that same speak method. This is what we call method overriding. The child effectively replaces the parent's generic behavior with its own specialized one. And this is where the magic really happens. Look at this loop. We're just telling each animal to speak. Notice what's missing? There's not a single if statement in sight checking if it's a dog or a cat. We don't have to. Python itself figures out which specific speak method to call at the very moment the code is running. That's called dynamic dispatch, and it is polymorphism in its purest form.
But Python has its own special flavor, its own philosophy, and it's captured perfectly in this famous saying. This idea is the secret behind Python's uniquely pragmatic and flexible approach to polymorphism.
Now, this is where things get really interesting. Take a look at these objects: a car, a bird, a person. They have nothing in common, right? They don't share a parent class or any formal relationship, but they all happen to have a method called .move. And for Python, that's good enough. Python says, I don't care what you are, I only care what you can do. If it has a .move method, I can treat it like something that moves. This is duck typing, and it's an absolute superpower.
You know the wildest part about all this? You've already been using polymorphism probably every single day you've coded in Python, and you might not have even realized it. It's baked right into the language, hiding in plain sight.
I mean, just think about the humble plus sign. When you give it two numbers, it does addition. When you give it two strings, it does concatenation. That's the exact same operator, the same interface, providing totally different behavior based on the type of objects you give it. This is a form of polymorphism we call operator overloading. And here's the cool part. This power isn't locked away just for Python's built-in types. You can do this too for your own custom objects. By implementing these special methods with the double underscores, we call them dunder methods, like _add here, we can literally teach our own vector class what to do when it sees a plus sign. It makes our code so much more intuitive. Okay, theory is great, but how does this actually help you build better software in the real world? Let's talk about building like a pro, using a polymorphic architecture. So let's say you're building an e-commerce site, right? You need a payment system. The polymorphic way to do this is to, first, define a common interface, maybe a base class called payment method. Second, you create your specific implementations, like a credit card class or a PayPal class. And third, you write your main logic, like your checkout function, so that it works with the general payment method, not the specific types.
And this is the whole point. This is the big win. Your core checkout function never, ever has to change. It just calls .pay. Tomorrow, your boss comes and says, we need to add Apple Pay. No problem. You add an Apple Pay class with a .pay method, and that's it. You don't touch the checkout function. It just works. That is the power of extensible design.
All right, let's bring it all home. We're going to recap the big ideas from this explainer and, just as important, point out a few common traps that beginners often fall into. So the number one red flag, the thing you want to avoid, is scattering if instance of all over your code. The moment you start manually checking an object's type, you're fighting against polymorphism, not using it. The whole point is to just trust that the object you have can do the job, whether it's through inheritance or because it's the right kind of duck. So to wrap it all up, here's your polymorphism cheat sheet. Remember the core idea: same name, different behavior. The main ways to get there are method overriding, where child classes get specific, and of course, Python superpower, duck typing. And the real-world goal here is to write code that's flexible, easy to extend, and free of that jungle of if-else checks. And that's a wrap. So I'll leave you with this question for the next time you sit down to start a project. Are you going to build a brittle system full of rigid checks and conditions, or are you going to use the power of polymorphism to build something that's clean, flexible, and truly professional? The choice is yours.
Hey everyone, and welcome. Today we're going to tackle a topic that's, frankly, a huge dividing line between just writing code and being a professional software engineer. We're talking about encapsulation. You know, if you really want to build Python code that's safe, reliable, and easy to maintain, this is a concept you absolutely have to nail down.
But before we get into the textbook definitions, let's just start with a simple question to get our heads in the right space. Imagine for a second, what if your data had absolutely no protection? What if any part of your code, anywhere, could just reach in and change a critical value with no rules, no checks, no nothing? Yeah, it sounds like total chaos, because it is.
I mean, look at this. A single, seemingly innocent line of code could cause an absolute disaster. Without any protection, someone could, either by accident or on purpose, set a bank account balance to a massive negative number. This one line is a gaping security hole, and it's the exact problem we're here to solve today with encapsulation.
So here's how we're going to break it all down. First, we'll look closer at the danger of this open code. Then we'll introduce the core idea of encapsulation. We'll see how Python handles it with its own unique rules. Then we'll level up from the manual way to the truly Pythonic way. And finally, we'll talk about the professional payoff, why this matters for your career.
All right, let's start with the danger of open code. That bank account example, that's not just some made-up problem. When your object's attributes are just out there, totally public by default, you have zero control. You can't enforce any rules, you can't validate any data coming in, and you're basically just hoping that nothing goes wrong. It's bad design, plain and simple.
So that brings us from the problem right to the solution, the principle of encapsulation. This is our main line of defense. It's a fundamental concept in object-oriented programming that was designed specifically to prevent the kind of chaos we just talked about.
So what is it exactly? Well, at its heart, encapsulation is really about two key things. First, it's about bundling. Packaging related data and the code that works on that data together into one neat little unit, an object. And second, and this is the really crucial part, it's about restricting direct access to some of that data, basically putting up a protective wall around it.
The perfect real-world analogy for this is an ATM. When you go to use one, you interact with it through a very specific, secure interface: the screen, the keypad, the card slot. You can't just pry open the machine and grab the cash or start editing the bank's database yourself, right? The machine controls your access and validates everything you do. That is encapsulation in a nutshell.
Okay, and this is a big one. We need to clear something up that trips up a lot of developers. Encapsulation is not the same thing as abstraction. Encapsulation is all about protection, hiding the data and controlling who gets to touch it. Abstraction, on the other hand, is about simplification, hiding all the messy, complex details behind a simple interface. Think of it like this. Encapsulation is what protects the car's engine, keeping all the complicated parts sealed away safely. Abstraction is the fact that you only need a steering wheel and two pedals to drive it.
All right, so that brings us to the practical part. How do we actually do this in Python? Well, this is where Python is a little different from languages like Java or C++. We don't have strict keywords like private or public. Instead, the Python community relies on naming conventions. Think of them as signals, or a kind of code of conduct from one developer to another about how an attribute is supposed to be used.
And these conventions are actually pretty straightforward. If a variable name just looks normal, like name, it's public. Fair game for everyone. If it starts with a single underscore, like underscore name, that's the developer giving you a polite heads up, like, hey, this is for the object's internal use. You probably shouldn't be touching this from the outside. But then you have the double underscore name. This is a much stronger signal, and it actually tells Python to do something special to stop people from messing with it by accident.
And that special thing is called name mangling. It sounds complicated, but it's not. When Python sees an attribute that starts with two underscores inside a class, it automatically renames it behind the scenes. So our double underscore balance inside the bank account class secretly becomes underscore bank account double underscore balance. Now this is a real lifesaver when you get into inheritance, because if a child class also tried to create its own double underscore balance variable, it would get mangled differently, which prevents it from accidentally stomping all over the parent's private data.
Okay, so hiding data is just the first step. The real goal is to control access. So now we're going to look at the good way to do this, and then we're going to look at the professional, the truly Pythonic way. This is where you really start to separate yourself as a developer.
The good way, and you'll see this a lot, is to create manual getter and setter methods. So you'd have a method called get underscore balance to read the value, and another one called set underscore balance to change it. And this works. It's not wrong. Inside that setter, you can put your logic, like checking to make sure the balance isn't negative. It gives you control, for sure, but it can feel a little clunky, a little verbose. It just doesn't feel very Pythonic, you know?
And that leads us to a really important question that all great programmers ask. Just because something works, does that mean it's the best way to do it? In a language like Python, where we care so much about clean, readable, elegant code, is there a better way?
Oh, you bet there is. The professional, the truly Pythonic way is to use the @property decorator. This is the gold standard. Why? Because it gives you all the power and control of those manual getters and setters, but it does it with a clean, beautiful syntax that makes it look like you're just accessing the attribute directly. And here is the absolute magic of it. To the person using your class, the code looks simple and direct. Account.balance equals 500. It feels totally normal. But what's happening under the hood? Python is actually intercepting that call and automatically running your special setter method, the one with the @balance.setter decorator, where all of your important validation logic lives. It is literally the best of both worlds, a super clean interface with powerful, controlled logic hiding just underneath.
So let's bring it all home. Why does mastering this stuff actually make you a better, more hireable engineer? It's because when you use these tools correctly, you're showing that you think about the bigger picture, about code quality, about security, about making things easier to maintain in the long run. You're not just hacking something together to make it work.
And in the real world, this is a superpower. You can enforce business rules like, hey, an employee's salary can never be set below the company minimum. You prevent that nasty data corruption we saw earlier. You put all your validation logic in one single centralized place. And you protect your class so that other parts of the code, especially subclasses, can't accidentally break its internal state. Your code becomes tough, reliable, and robust.
So this brings us to a simple checklist for writing professional-grade Python. Use a single underscore for things that are meant for internal use. Use the double underscore to really protect critical data, especially from those inheritance conflicts. Always use @property when you need to control access to an attribute. Make sure you put your validation logic inside those setters. And here's the golden rule. Never expose the internal guts of your objects if you don't absolutely have to.
And hey, if you are ever in a job interview and you get asked about this right here, this is your golden ticket answer. Saying this shows that you don't just know a textbook definition. It proves you understand how it's done in Python, why it's done, and what tools you use to do it. It shows you think like a real engineer.
Because ultimately, every class you write, every line of code you commit, it tells a story about you as a developer. By using encapsulation the right way, you're choosing to tell a story of security, of control, and of true professional craftsmanship. So the only question left is, what story will your next piece of code tell?
All right, let's talk about one of the most practical skills you can learn in Python, file handling. We're going to unlock how to make your programs read, write, and most importantly, how to make them remember things. You know, it kind of feels like magic, right? But it's not. The secret is all about handling files. This is what takes a piece of software from being just a temporary tool to something that really becomes a part of your digital life. Okay, so let's really dive in and get our heads around this. When we say file handling, what are we actually talking about? What does it really mean for the code you write? To put it simply, it's how your Python code can create, read, and mess with files. Think of it as the bridge between your program's short-term memory and your computer's permanent storage. Without it, every single time you ran a program, it would be like starting over from scratch. Now, in Python's world, you're mostly dealing with two types of files. You've got your text files, which are exactly what they sound like, stuff we can actually read. And then you have binary files. These are a whole different beast. Think images, audio files, you name it. They're not for us to read, they're for the computer to understand. So before we can do anything at all with a file, we need the key to unlock it. We have to open it. And believe me, there's a right way and a very, very wrong way to do it. When you open a file, you have to tell Python what you plan to do. You use a mode for this. Think of it like telling a bouncer your intentions. Are you just here to look around? R for read. Or are you planning to W for write, which could change everything? Or maybe you just want to A for append, to tack something on at the end.
And here it is, the golden rule you absolutely need to remember. Always use the with statement. See, the old way of opening and then manually closing a file is just risky. If your program hits an error, that file could be left hanging open, and that can lead to corrupted data. The with statement is your safety net. It guarantees that the file gets closed properly, no matter what happens.
All right, so now that we know how to safely open the door to a file, let's get into the two main things you'll be doing: pulling data out of a file and putting new data into it. So Python gives you a few different tools for reading. If it's a small file, you can use .read to just slurp the whole thing up at once.
But for bigger files, it's usually smarter to use .readline to zip it one line at a time, or maybe .readlines to get all the lines neatly organized into a list. Okay, listen up, because this part is super important. When we talk about writing to a file, using the W mode is like taking a bulldozer to it. It completely flattens whatever was there before. If you just want to add a new entry at the end, you absolutely have to use A for append. It's way safer if you want to keep your old data. We've covered the basics, but Python's power goes way beyond simple text. It also gives you some really precise, fine-grained control over how you work with pretty much any file type.
Hey, remember those binary files we mentioned earlier? Well, working with them is actually super simple. You just add a B to your mode. So R becomes RB for read binary, and W becomes WB for write binary. That's it. It just tells Python, hey, treat this as raw bytes, not text. And this brings us to a really cool idea. Python always knows exactly where it is inside a file. It uses something called a pointer, which works just like the blinking cursor in a text document. It keeps track of where the next read or write operation is going to happen. And the best part, you can control that pointer. The .seek function is basically your superpower for file navigation. It's like having a bookmark. You can read a few characters, then use seek 0 to instantly jump right back to the beginning of the file and read it all again. It gives you total control. Finally, let's get into the practical, real-world stuff, how to actually manage these files, and more importantly, how to prepare your code for when things, inevitably, go wrong. To handle files on your actual computer, Python gives us the built-in OS module. It's always a good idea to check if a file even exists with os.path.exists before you try to open it. And when you're done with the file for good, os.remove gets rid of it. But be careful, there is no recycle bin for this command. When it's gone, it's gone. Now, if you want to write truly professional, robust code, you need to wrap your file operations in what's called a try-except block. This is your ultimate safety net. It lets you try to do something, like open a file, and if an error happens, like the file isn't there, your program won't just crash and burn. Instead, it'll jump to the accept block and handle that error gracefully. So if you only take away a few things from all this, make it these 3. 1, always use the with statement. It's just safer. 2, know the difference between W for write and A for append so you don't accidentally delete your data. And 3, use try-except blocks to build code that doesn't fall apart when it hits a little bump in the road. Now that you have this power, seriously, the possibilities are endless. You can build programs that keep logs, save user settings, or even create your own simple databases. That barrier between your program and the real world, it's gone. So the real question is, what are you going to build with it?
All right, let's talk about a skill every single Python developer needs, handling files. But we're not just going to cover the basics today. We're going to look at how to take your code from something that just works to something that's truly professional and ready for the real world.
Think about it. In almost any app you build, you're dealing with files. Logs, configuration, user data, it's everywhere. Getting this right is what separates a fragile script from a rock-solid, reliable application. So let's make your code great.
First things first, let's talk about the #1 most important rule of handling files in Python. You've got to use the with statement. It's the gold standard and for a very, very good reason.
And the difference is, well, it's night and day. Just look at this. On the left, you've got the old manual way, where you have to open the file and this is the important part, you have to remember to close it. On the right, though, that's the pro way. It's cleaner, it's simpler, and it handles all the cleanup for you, automatically.
So why is this such a big deal? Well, the with statement guarantees that your file gets closed, even if your code hits an error. And that little guarantee prevents all sorts of nasty problems, like memory leaks or even corrupting the file you are working on. It's not just about saving a line of code, it's about writing fundamentally safer, more reliable software.
Okay, we've got the golden rule down. Now let's tackle the most common type of file you'll ever encounter, the simple text file. But we're going to go beyond just opening and reading. We'll see how to handle them like a pro, especially when things get big.
And here's a classic mistake a lot of us make when we're starting out. On the left, using .read tries to load the entire file into your computer's memory. Now, if that's a small config file, no problem. But what if it's a multi-gigabyte log file? You're going to crash your program, guaranteed. The best practice, on the right, is to process the file line by line. It's way more memory efficient and the only sane way to handle large files.
Oh, and here's a pro tip that will save you from so many headaches down the road. Always specify the encoding. UTF-8 is pretty much the universal standard today. If you forget this, the moment your code sees a special character or text from another language, you're going to get some really weird, hard-to-debug errors. Just make it a habit.
All right, moving on to structured data. CSV files are everywhere, right? From data science to business reports. But they come with a very, very common trap, and we're going to learn exactly how to avoid it. This looks so simple and so tempting, doesn't it? Just grab a line from the file and split it by the comma. And you know what? For super simple data, it might even seem like it's working. But trust me, this approach is a ticking time bomb.
And here's the explosion. What happens when your data has a comma inside one of the values, like London, UK? Well, your simple split call is going to get it wrong. It'll split that city into two separate pieces, and suddenly all your data is misaligned and completely useless. That's why the manual way is so dangerous.
So, what do? We use the right tool for the job. Python comes with a fantastic built-in CSV module that was designed specifically for this. It's smart. It understands things like quoted fields, commas inside your data, and all those other tricky edge cases, so you don't even have to think about them. So now we know what tool to use. Let's level up again and see how to use it to write code that isn't just correct, but is also super efficient, easy to read, and safe. This is the Professionals Toolkit. Now this is a total game changer for readable code. Instead of accessing data with a clunky index like row 0 dict reader lets you use the actual column headers as keys, like row name, your code instantly makes more sense. And the same idea works for writing files too. With csv.dictWriter, you can write data from a list of dictionaries, and it makes sure your headers and data always line up perfectly. So what's happening under the hood? It's actually pretty brilliant. DictReader takes each row, which is just a list of strings, and it uses the header row to intelligently map it into a dictionary. It turns this abstract list of data into a meaningful structure that's so much easier to work with.
Here's another mark of a pro. Professional code doesn't just crash. It anticipates problems and handles them gracefully. What happens if the file you're trying to open just isn't there? Wrapping your file operations in a try-except block is your safety net. It catches that file not found error and lets you handle it, making your application robust and user-friendly instead of just broken.
Okay, that was a lot, so let's pull it all together. We're going to create a final, code-ready checklist to make sure all these best practices really stick. First, a quick decision guide. When should you use a plain TXT file versus a CSV? Simple. Use text files for unstructured stuff, logs, notes, config files. But the moment you have data that fits into rows and columns, anything that would look at home in a spreadsheet, CSV is absolutely the way to go. And here it is, your final checklist of things to avoid. Don't forget the with statement. Don't you dare parse CSVs with .split comma. Never load a huge file into memory all at once. And a couple of final tips. When you're writing a CSV file, always specify your UTF-8 encoding and remember to add new line equals empty. That little trick prevents weird blank rows from appearing in your output file. Nail these, and your code will be in fantastic shape.
So there you have it, a professional toolkit for handling two of the most common file formats out there. You've got the tools, you know the techniques. The only real question left is what are you going to build with it? What data story are you ready to tell? Thanks for joining me.
All right, we're not going to waste any time with abstract theory here. This explainer is all about one thing, the practical, hands-on Python skills that actually get you hired. So if you want to go from just learning Python to earning with Python, you are in exactly the right place. Let's dive in.
So let's say you're learning Python. Your big goal is to land that first developer job, right? You've probably got loops and functions down, maybe even dipped your toes into object-oriented programming. But what's the next step? What's that one practical skill that interviewers are always looking for?
Well, here it is. You absolutely positively must master how your Python code interacts with the real world. And that means handling files and dealing with data. Seriously, this isn't some nice-to-have skill on your resume. It's a non-negotiable must-have requirement for pretty much every backend, data, or automation job out there. Okay, first things first, let's build the foundation. We're going to cover the absolute essential mechanics of how Python opens, reads, and writes to files.
You know, at its core, file handling is exactly what it sounds like. It's how your Python script can save its progress, or read secret keys from a config file, or process a bunch of user data. It's what makes your programs persistent and powerful.
Now you really got to pay attention here because one single letter can literally make or break your entire program. R is for read. That's simple enough. But if you use W for write, you will completely erase everything that was already in the file. Poof, gone. If you just want to add to the end of a file, you have to use A for append. Getting this right is absolutely critical.
This right here, this is one of the biggest signs that separates a beginner from a professional Python developer. Yeah, you can open a file and then try to remember to close it manually. But the real pro standard, what employers expect to see in your code, is using the with statement. It handles closing the file for you automatically and safely. No bugs, no resource leaks.
And speaking of writing solid code, what happens if the file you're trying to read just isn't there? Or maybe you don't have the right permissions to open it. Your program will crash. End of story. That's why wrapping your file operations in a try-except block to catch errors like a file not found error is another one of those non-negotiable skills for code that's ready for the real world.
Okay, with that foundation in place, we are ready for the main event, JSON. Look, if basic file handling is the concrete foundation, then JSON is the skyscraper you build on top of it. It is the universal language of data on the modern web.
JSON stands for JavaScript Object Notation. But don't let that name fool you. It's used absolutely everywhere, not just in JavaScript. It's just a simple, text-based way to structure data that's super easy for both humans and computers to understand. If you've ever used a weather app that pulls in the forecast from some server, yep, you've used JSON.
At first glance, JSON looks almost exactly like a Python dictionary, which is what makes it so powerful. But, the devil is in the details. JSON needs lowercase true, false, and null, not Python's capitalized true, false, and none. And here's the big one that gets everyone. All strings and keys in JSON must use double quotes. Single quotes will throw an error every time.
So how do we cross that small bridge between a Python dictionary and a valid JSON object? Well, the great news is that Python absolutely loves JSON. It comes with a built-in module that makes working with it incredibly simple. When we go from a Python dictionary to JSON, we call that serializing it. Just think of it like packing your Python data into a universal travel adapter. The built-in JSON module gives you two main tools for this. JSON dumps S, and that S is important, it stands for string, which creates a JSON string right there in memory. And then there's JSON dump, which writes your data directly into a file for you. And hey, here's a little pro tip that interviewers love to see. Whenever you're writing JSON to a file, always add the indent equals 4 argument. This is what we call pretty printing. It takes the JSON from a single, unreadable line of text and turns it into this beautiful, clean structure that's super easy for any human to read and debug. And going the other way from JSON back into Python is called deserialization. It's basically unpacking the data. The pattern is exactly the same, just in reverse. You use JSON.loads, again with an S, to parse a JSON string from memory, and you use JSON.load to read a whole JSON file and instantly convert it into a Python dictionary that you can start working with.
So, we've gone through the technical bits. We know how to do it. But let's talk about the payoff. Why is mastering JSON one of the absolute fastest ways to level up your Python career?
It's because in any modern developer job, you will live and breathe JSON. It's just a fact. Whether you're building a web app with Django that needs to talk to a front end, or you're pulling data from an API, or you're just reading a simple config file, JSON is the common thread. It is everywhere. So, let me be super clear about this. The examples we just walked through, they aren't just some abstract exercises. They are a direct look at the kinds of tasks you will be doing day in and day out as a professional Python developer. And because this stuff is so fundamental, you can bet that hiring managers are going to test you on it. They'll ask you these exact questions in a technical interview. Knowing the difference between dump and dumps isn't just trivia. It's a litmus test to see if you have real, practical, hands-on experience. Okay, we've covered a ton of ground, so let's boil it all down into a simple, actionable checklist you can take away with you.
Here's your cheat sheet for writing job-ready code. Number 1, always use the with statement for files. Number 2, know the difference between the file versions, dump and load, and the string versions, dumps and loads. 3, always expect things to go wrong and handle those errors. And 4, just remember, JSON is almost a Python dictionary, but it has a few very strict rules you gotta follow.
Look, mastering these concepts is what takes you from someone who just knows Python syntax to someone who can build real, data-driven applications. So the only question left is, now that you've got these powerful tools, what are you going to build with them? We've all been there, right? You're coding along, everything's going great, and then, bam, your program just crashes. It's that sinking feeling. But what if I told you that you could actually anticipate those crashes and tell your program exactly how to handle them with grace? Well, that's what we're going to do today. Let's dive in and turn you from a victim of errors into a master of your code with Python exception handling.
So let's start with a question we all know the answer to, unfortunately. You've written your script, you hit run, and nothing. Everything just grinds to a halt. You're just staring at a wall of angry red text, and your program is completely dead in the water. It's so frustrating, right? But what's really happening under the hood? Well, your program has just hit a problem it has no idea how to solve.
Take a look at this super simple line of code. We're asking Python to do something that's, well, literally impossible. Divide 10 by 0. Even before you run it, you can feel that this is going to cause some trouble. This is the perfect classic example of code that is absolutely destined to fail.
And boom, there it is, the zero division error. That one line of text is enough to bring your entire program to a screeching halt. This is exactly what happens when an error goes unhandled. But don't worry, we're about to learn how to catch it.
You see, this crash isn't just a random event. It has a formal name in Python. It's called an exception. I like to think of it as your program throwing its hands up in the air and just yelling, "I can't do this! I don't know what to do!" And understanding what an exception really is, that's the first step to taming it.
So here's the core idea. An exception is just an error that pops up while your program is running. Now the key phrase here, the most important part, is if not handled. Because an unhandled exception means your program crashes. But a handled exception, that's a program that keeps on running smoothly, just like you wanted it to. Okay, so how do we actually build this safety net? How do we handle these things? Well, let me introduce you to your new best friend, the try and except block. This is your first and, honestly, your most powerful tool against unexpected crashes. This comparison says it all. On the left, you've got the code that just blows up. On the right, look what we did. We wrapped that same exact risky line of code in what's called a try block. Now, when Python hits that zero division error, instead of crashing, it just jumps down to the except block and runs that code instead. No crash, just a clean, controlled response. And the logic behind this is beautifully simple. Think of it like you're driving down a road. The try block is your main highway. You're just cruising along. The accept block? That's a planned detour. If you hit an unexpected roadblock, an error, you just calmly take the detour. But if there's no roadblock, you never even see the detour. You just keep on going. Simple as that.
But we can get way more sophisticated than just a single detour. I mean, what if there are different kinds of roadblocks? A flat tire is different from a bridge being out, right? Python gives us the tools to handle different errors in different ways, and even to do things only when everything goes right, or to do cleanup no matter what happens.
So check this out. Inside this try block, we've basically set up two potential landmines. First, it tries to turn the letters A, B, C into a number. That's never going to work. It immediately triggers a value error. The code jumps straight to the accept value error block, and that's it. It doesn't even get to the next line to try dividing by 0. The first error that happens is the only one that gets caught.
Now, you can also just throw out a giant catch-all net. The general exception will catch almost any error that comes its way. This is pretty handy for logging errors you didn't expect, like we're doing here with that little variable e. But, and this is a big but, you have to use this with caution. If you use it too much, it can actually hide bugs and make your code fail silently when it should be telling you something's wrong.
Okay, this table right here. This is your ultimate cheat sheet for the whole structure. You already know try for the risky stuff and except for when it goes wrong. But look at the additions. There's an else block, which is like a little victory lap. It only runs if the try block succeeded perfectly. And then there's finally. Think of finally as the cleanup crew. It runs always, whether there was an error or not. It's absolutely essential for things like closing files or database connections.
So far, we've pretty much been playing defense, just reacting to the errors that Python throws at us. But true mastery comes when you start playing offense. You get to define what counts as an error in your own application, which makes your code way safer and clearer about what it needs.
Take a look at this check age function. Syntactically, the code's fine, but our application has a business rule. You have to be 18 or older. So, by using the raise keyword, we can enforce that rule ourselves. We are intentionally creating an error if the age is too low. We're not just reacting anymore, we're proactively making our code more robust.
And it gets even cooler than that.
You can invent your own error types from scratch. By creating a new class that inherits from exception, like our custom error here, you can make your error handling incredibly specific to your program. Imagine you're building a banking app. You could create an invalid transaction error or a user not found error. It makes your code so much easier to read and debug.
Okay, so we've covered all the tools in the toolkit. We've got try, except, else, finally, and raise. Now let's put it all together. How do the pros use these tools to write code that's practically crash-proof? Well, it all comes down to a few key best practices.
So here it is, your checklist for writing professional, robust code. First, always try to catch specific errors, not just the giant exception net. Second, use finally for any cleanup that absolutely must happen. Third, and this is a big one, avoid bare except clauses. They can swallow up real bugs and leave you scratching your head. Fourth, log your exceptions so you can debug them later. And finally, don't be afraid to raise your own exceptions to enforce your code's rules. And that pretty much brings us to the end. You now have the entire toolkit to take complete control over your code when things go wrong. So the question I have for you is this. As you go back to your own projects, what unexpected errors are you going to prepare for now? Maybe a file that doesn't exist, bad input from a user, or some invalid data? Go turn those potential crashes into controlled, predictable outcomes.
All right, let's dive into something that every single programmer deals with, errors. We're going to talk about how to take our Python code from being super fragile, the kind that shatters at the first sign of trouble, into something that's totally robust and can handle the unexpected with grace and control. I mean, we've all been there, right? You've been coding for hours, you finally hit run, you're kind of holding your breath, hoping everything works, and then something goes wrong. And sometimes it's a line of code that looks so innocent. Look at this. Result equals 10 divided by 0. We're just doing some simple math. What could possibly go wrong? Well, as you know, in programming, sometimes the simplest looking lines are hiding a tiny little time bomb.
And bam, just like that, your program grinds to a halt. It crashes completely and spits out this big, scary error message. This one is a 0 division error, and it just stops everything cold. The normal flow of your program is dead. But what if there was a way to see this coming? A way to catch it before it blows everything up?
Well, there is, and it's called the try/except block. You should really think of this as your code's safety net. It's the built-in tool Python gives us to actually anticipate and manage these kinds of program-stopping meltdowns. So that thing that crashed our program, that has a name. It's called an exception. It's basically an error that pops up while the program is actually running. And the key word here is handled. See, if we don't handle it, the program dies. But if we do handle it, well, then we're in control. And this really shows the difference, right? On the left, you've got that uncontrolled crash, the big explosion we just saw. But look over on the right. By wrapping that same exact code in a try/except block, we handle the error. We stop the crash, and instead, we can do something else, like print a nice friendly message. The program keeps going. Okay, but the control doesn't even stop there. The basic try/except is awesome, but we can get even more specific, even more powerful, by adding 2 more parts, else and finally. So here's how the whole thing flows. First, Python is going to try to run that risky piece of code. If something goes wrong, it immediately jumps down to the except block. But what if nothing goes wrong? What if it works perfectly? Then it skips except and runs the else block instead. And then no matter what, whether it worked or it failed, it will always run the finally block at the very end. Yeah, so the thing to remember about else is that it's your success path. It's the code that only runs if the try block made it through without any problems at all. This is great because it keeps your everything went right logic totally separate from your error checking code. It's just cleaner. And finally is your ultimate cleanup crew. Seriously, did you open a file? Did you make a connection to a database? The finally block is the guaranteed place to close those things. This is so important for apps that need to run all the time because it stops resource leaks that can, slowly kill your entire system. All right, so we've got the basics down. Let's level up a bit and look at some more advanced ways to handle different kinds of errors. So what happens if your code can fail in a bunch of different ways? Well, you can handle each one differently. You can have one except block for a value error and another one for a 0 division error. Or if you want to treat them the same, you can just group them together like you see here. It gives you super precise control over how you respond to different problems. Sometimes just knowing an error happened isn't enough. You really want to know why. So you can actually capture the exception object itself using as e. This little e variable now holds all the details about what went wrong. It's perfect for logging the error or showing a really helpful message back to your user. And get this, you don't have to wait for Python to find an error. You can actually make one happen yourself. You do this with the raise keyword. This is awesome for when something isn't technically a Python error, but it breaks one of your rules. Like say if a user tries to enter a negative number for their age, you can just raise a value error and say, nope, that's not allowed.
Okay, we've covered a lot of ground here, so let's boil it all down to a few simple, really powerful best practices. Think of these as the rules of the road for writing solid exception handling. All right, here are the big ones. First, keep your try blocks small. Only put the 1 or 2 lines in there that might actually fail. Second, be specific. Don't just catch a generic exception, because that can hide bugs you didn't expect. Catch the specific error you're looking for. Third, use that else block to keep your success code clean and separate. Fourth, and this is a big one, always use finally for cleanup. And last but not least, log your exceptions. It'll make debugging so much easier later on. Okay, theory is one thing, but let's see how all of this actually comes together in a real-world example to build a program that's truly resilient.
So let's imagine our program needs to open and read a file that a user gives us. I mean, what could go wrong? A lot, actually. Maybe the file doesn't even exist. Or maybe it does, but we don't have permission to read it. Let's build a safety net to handle both of those cases. Okay, here's how we'd build it. First, in our try block, we attempt to open the file. Now, if the file isn't there, we'll jump to the except file not found error block and handle that. If the file is locked and we can't access it, we'll hit the accept permission error block instead. But if everything goes perfectly, we'll run the else block to let the user know it was successful. And you can see, no matter which path we take, we always end up in the finally block to wrap things up. This makes our program super robust. It just won't crash. And just to wrap it all up, here's a quick little cheat sheet for you. Try is where you test your risky code. Accept is where you handle the problem. Else is your success code. Finally is for cleanup no matter what. And raise is for when you want to create your own error. Simple as that. So think about where we started. We went from a program that would just crash at the slightest problem to one that can gracefully handle all sorts of unexpected issues. The big takeaway here is that errors aren't just things to be afraid of. They're events that we can and should manage. So the next time you're writing code, just ask yourself this. You know the unexpected is going to happen. How are you going to prepare your code for it?
All right, let's talk about leveling up our Python skills. We're going to move beyond writing those simple scripts that, work most of the time and start building professional, truly resilient applications that know how to handle the unexpected. Let's dive in.
So, I'm sure you've been here. You write some code, you run it, you're feeling pretty good about it, and then, bam, the whole thing just stops, and your screen is suddenly filled with this wall of angry red text. It's something every single developer has felt, but it's also something we can absolutely get under control.
This right here is a traceback, and it's basically Python's way of screaming that something went terribly wrong and it had no idea what to do. In this case, it was a zero division error. Now, for a quick little script, this is, annoying, but for a real application that's out in the world, this is a catastrophic failure. The program just hit a brick wall and gave up.
And this is what we're talking about today, what I call the code crash problem. It's all about code that's fragile. Code that works great when everything is perfect, but just shatters the second it runs into something it didn't expect. Our mission is to build something way stronger.
Okay, the key to solving this is really a mental shift. We've got to stop thinking of these things as just errors. An exception is an event. It's a signal that something unusual happened. And the best part is, Python gives us the power to intercept or catch that event and decide what to do, instead of just letting the whole thing burn down.
So how do we actually catch these events? Well, our first line of defense is what's called exception handling. And I want you to think of the try except block as the airbag for your code. Yeah, a collision might still happen, but the airbag deploys to prevent total system failure, letting the program continue on in a controlled, safe way.
So how does this airbag work? It starts with the try block. This is where you put the risky code. Anything that you suspect might fail. Maybe it's a network request, a file operation, or in this case, some sketchy math. You wrap it inside a try block. You're basically telling Python,
Hey, keep an eye on this next part. And this is the airbag deploying. When that risky code inside the try block fails, the program doesn't crash. Instead, Python jumps immediately to the except block. It's our safety net. We've caught the specific error, and we get to run our own code instead, completely avoiding a total shutdown.
Now, this system is actually a full-blown toolkit. You've got try and except, which we've seen, but there's also an else block, which is cool because it only runs if there was no error at all. And then you have finally. This one is super important. The code in the finally block will always run, whether there was an error or not. It's perfect for cleanup tasks, like closing a file or a database connection.
So this is great, right? Our application doesn't just fall over anymore. It's resilient. But hang on, we have a new problem. The program just quietly handled an error and moved on, and all we got was a little print statement that disappears forever the second the program closes. How on earth are we supposed to figure out what went wrong days or even weeks later?
And this brings us to Level 2, Professional Logging. If exception handling is the airbag, then logging is the black box flight recorder for your application. It's a system that records everything, events, warnings, and especially errors, so you have a permanent detailed record of exactly what happened, when it happened, and why.
This chart really nails the difference. Using printf can kind of like shouting into the wind while you're debugging. It's temporary, it has no context, and it's gone forever once you close the terminal. But the logging module, that's the professional tool. It's persistent, it saves to a file, it adds crucial info like timestamps and severity levels, and it's totally configurable.
And logging comes with these built-in severity levels. Think of this like setting the sensitivity on your black box. While you're developing, you might want to see everything, so you set it to debug. But in a live production app, you might only care about warning and above. This lets you cut through the noise and focus on the real problems.
And setting this up is actually really straightforward. All you have to do is import the logging library and run this basic configuration. You just tell it what file to write to, what the minimum level of severity is that you care about, and how you want each log message to be formatted. Just like that, you've got a permanent record of your application's life.
So we have the airbag to stop the crash, we have the black box to record what happens, now it's time for the main event, putting them together. This right here, this is the pattern that separates hobby projects from truly professional, resilient software.
And here it is, the pro-level synthesis in action. It's so simple and so powerful. The try block does its thing. When the error happens, the except block catches it, preventing the crash. But instead of just printing a useless message, it calls the logger. The airbag deploys, and it immediately tells the black box to start recording. Now, the real magic is this one specific command, logging.exception. This isn't just a regular log message. When you use this inside an except block, it's special. It automatically knows an error just happened, and it grabs the entire error traceback for you and puts it right into your log file. No extra work needed.
And this is the glorious result. This is what you see in your app.log file. Look at all that beautiful information. You've got a timestamp, you know it was an error, you have your own custom message, and, most importantly, you have the full detailed traceback showing you exactly what line of code broke. This is absolutely priceless for debugging a live application.
Whew, all right, we went all the way from crashing code to a really robust system pretty quickly there. So let's just do a quick summary of the key takeaways to make sure this all sinks in. So here's the pattern. First, exceptions are your airbags. Use try except to handle errors gracefully so your app doesn't die. Second, logging is your black box. Ditch the temporary print statements and use a real logger. And finally, the pro move is to combine them. You catch an exception, and then you use logging.exception to record it perfectly. Your program stays alive, and you get a perfect record of the error. Best of both worlds.
So I'll leave you with this final thought. Your code will encounter the unexpected. It's not a possibility, it's an absolute guarantee. And when it does, what's it going to do? Is it just going to crash and burn, leaving you totally in the dark? Or is it going to handle that event gracefully and leave you a detailed report that informs you exactly what you need to fix? The choice really is yours.
All right, if you're serious about becoming a Python developer, I mean really serious, then this is one of the most important explainers you're going to see. We're going to cover the one concept that truly separates simple little scripts from professional, large-scale applications. Okay, let's get right into it. So just think about it for a second. How on earth do apps like Instagram or Spotify keep millions of lines of Python code from becoming a complete and total nightmare? I mean, it's not magic, right? it's all about architecture. And the answer is actually surprisingly simple, but it's also incredibly powerful.
Yep, that's it. That is the secret. Modules are the absolute bedrock, the fundamental building blocks of pretty much all real-world Python software. And by the end of this, you'll know exactly how to use them like a pro. So let's start with the absolute basics. We're going to pull back the curtain on these secret building blocks and really get to the heart of what modules are all about.
It really is that simple. Don't overthink it. A module is just a Python file. Any file that ends in .py. Anything you decide to put in that file, a function, a variable, a class, can now be picked up and reused anywhere else.
Let's make this super concrete. So imagine you create a file, let's call it math.tools.py. Inside, you just write some simple math stuff, maybe a function to add two numbers, and you define the variable pi. And boom, just by saving that file, you have created a fully functional Python module. It's now this little self-contained block of code, ready to be used wherever you need it. So why is this so critical? Why do we care? Well, because modules force you to be organized. They let you reuse code without that terrible copy-pasting we all do at the beginning. They keep different parts of your program clean and separated. And honestly, they're the only way to write professional software that can actually grow and scale. Okay, so you've created this cool module. Now what? How do you actually use it in another file? Well, that's where importing comes in. The best way to think about it is like opening your coder's toolkit and just grabbing the specific tool you need for the job.
So you've basically got three main ways to do this. First, a basic import. This is like grabbing the entire toolbox. Then there's a specific import where you just grab one single tool you need, like the square root function. Or, and you're going to see this one everywhere in professional code, you can use an alias import, where you rename something to make it shorter, like changing numpy to just np. This is a total pro move to keep your code clean and super readable.
Now, here's the cool part. Python gives you a huge head start. It comes packed with a massive standard library of modules that are ready to go. But the real power, that comes when you start building your own. Let's see how that works. Right out of the box, Python hands you these incredible tools. You've got the math module for any kind of calculation, random for when you need, randomness, and datetime for handling anything to do with dates and times. And these are just a few examples of what's at your fingertips before you even install anything else. But this is where you really level up. Making your own module is just a simple three-step process. 1. Create a file, let's say calculator.py. 2. Add your code, your functions. And 3. In your main program, just import it and start using it. This little loop right here, this is how real applications are built, piece by piece, module by module. Okay, now that we have the building blocks, let's talk about scaling up. We're getting into the techniques that really separate the beginners from the pros. We're talking professional-level organization and reusability.
So once you start creating a bunch of modules, you need a way to organize them, right? Otherwise, it's a mess. And that's exactly what a package is. It's just a folder that you use to group related modules together. It's like going from one messy toolbox to a beautifully organized set of drawers. Okay, everybody listen up, because this next concept is probably one of the most important tricks in all of Python, and it comes up in interviews all the time. You'll see this line of code everywhere, if_name equals _main. Here's what it does. It allows a single file to do two different things. If you run the file directly, all the code inside that if block will run. But if you import that file as a module into another script, the code inside that block won't run. This is absolutely essential for creating tools that you can reuse without them accidentally running code when you don't want them to.
All right, let's bring this all home. We've talked about the what and the how. Now let's talk about the best practices, the things that will really define your career as a Python developer. Think of these as the rules of the road. Keep your modules small and focused. Each one should do one thing and do it really well. Give them clear names so you know what they do. And please avoid circular imports. That's where module A imports B and module B imports A. It's a recipe for disaster. And that /name equals /main trick we just talked about, that helps with that last point. So why does all this matter so much for your career? Because a deep, solid understanding of modules is foundational for over 90% of Python jobs. It doesn't matter if it's web development, data science, automation, modules are the backbone of everything.
And I really want to leave you with this thought. This isn't just a nice-to-have skill, it's an absolute necessity. Without a firm grip on how to structure your code with modules and packages, trying to build any kind of large-scale application is, well, it's basically impossible.
So as a final check, take a look at these questions.
These are the exact kinds of things that will come up in a technical interview. If you can confidently answer them, you are in a fantastic spot. And based on what we just covered, you know a module is a file and a package is a folder. You know that _name == main trick, and you know the different ways to import. You've built a really solid foundation.
So there you have it. You now understand the fundamental principle of Python architecture. You've just been handed the architect's blueprint, the same one used to build these massive, world-class applications. So, the only question left is, what are you going to build first? Have you ever written a Python script and just wondered how that little text file can actually reach out and do things on your computer? Well, that's the magic we're getting into today. We're going to look past the usual stuff and dive into two of Python's most powerful built-in modules, OS and Sys. Trust me, getting a grip on these is what turns your code from a cool idea into a real-world tool. Think about it. Your code is kind of stuck in its own little world. So how do we let it out? How does it actually read a file from your desktop, or listen to commands you type in the terminal, or even just know what kind of computer it's running on? That's the puzzle we're going to solve. And the solution comes down to these two modules working together. Here's the easiest way to think about it. The OS module gives your script hands, right? It lets it touch and move and change files and folders. The SYS module, on the other hand, gives it a brain and a voice. It lets the script understand itself and listen to the instructions you give it. Okay, let's start with the OS module. This is where your code really gets its hands dirty. It's how your script reaches out of that digital box and starts messing with the actual file system on your machine. This is the secret sauce for any kind of serious automation. So, what can you actually do with it? A ton. You can make new folders, delete old files, rename things, all with a single line of Python. You can ask, hey, where am I running from right now? And os.getCWD will tell you. You can peek inside a folder with os.lister. And this is a big one. You can access environment variables. That's where you store secret stuff like API keys so you don't have to hard code them in your script. Super important. Now let's talk about a classic mistake. I'm pretty sure we've all done this at some point. You need to build a file path, so you just add the strings together with a slash in the middle. It makes perfect sense, and hey, it even works. Until it totally doesn't. And here is the professional, much smarter way to do it. You use os.path.join. You just give it the parts, the folder, the file, and it figures out the rest. It's cleaner, it's safer, and it just works. So why is this such a big deal? Well, because your code might run on different computers, and not all computers speak the same language. See, Windows uses a backslash for its file paths, but Mac and Linux, they use a forward slash. If you hard code one or the other, your script is going to break on a different system. os.pathjoin is like a universal translator. It automatically uses the right slash for whatever computer it's on. This is non-negotiable for writing code that works everywhere. All right, so our script has hands, thanks to the OS module. Now it's time to give it a brain and a voice with the SYS module. This one is all about self-awareness. It lets your script understand the context it's running in and, well, listen. You know, you don't always want to have to open your script and change the code just to get it to do something a little different. A much better way is to give it instructions from the outside, from the command line, just like this. Those extra words, hello and world, are what we call arguments. They're the instructions we're passing in. So how does the script hear those instructions? Well, the magic behind that is something called sys.argv. As soon as you run your script, Python creates this special list called argv, and it stuffs everything you typed on the command line right into it. It's your script's ear to the outside world. So let's break down what that list actually looks like. The very first thing, at index 0, is always the name of the script itself, script.py. Then the next thing you typed, hello, that's at index 1. And the next one, world, is at index 2. It's that simple. It's just a list of the words you typed in order. But Sys can do way more than just listen. It's like your script's control panel. If something goes wrong, you can hit the big red button with sys.exit to stop everything. If you're having trouble importing another module, you can check sys.path to see exactly where Python is looking for it. You can even check which version of Python is running, which is super useful. Okay, we've met the individual players. We know what OS does, we know what SysYS does, but the real magic happens when they work together as a team. So let's look at a real-world example to see this power duo in action. So here's our goal, something you might actually need to do. We want to write a simple tool that lets a user type in a folder name, and our script will list out all the files inside that folder. Simple, practical, and a perfect job for our 2 modules. So check out this workflow. First, the user runs the command. The Sys module immediately jumps in, and sys.argv grabs that word documents. Now Sys hands that over to the OS module. OS takes documents and first checks, hey, does this folder actually exist, using os.path.exists? If it does, great. Then os.lister goes into that folder and grabs a list of all the file names. And finally, the script just prints that list out. See that? It's a perfect handoff. Sys listens and OS acts.
So let's just recap this one more time. It's all about a clear division of labor. Anything to do with the file system, files, folders, paths, environment variables, that's a job for the OS module. But anything to do with the script itself, command line arguments, exiting the program, how the Python interpreter is behaving, that's all Sys. Knowing which tool to grab for the job is what makes you a pro.
Okay, this is cool, but why does this really matter? Because this stuff right here isn't just a neat programming trick. This is a career booster. This is the kind of knowledge that takes you from someone who just messes around with Python to someone who can get hired to use it.
Seriously, go look at job descriptions for DevOps or automation or backend engineering. This is what they're asking for. They need people who can write scripts that interact with the system, that can be automated, that can be run from a command line. In these fields, knowing OS and Sys isn't just a nice to have. It is literally the price of admission.
So, what's the next step? Don't just watch this, go build something. Start small, build a little command line tool that organizes your downloads folder, or one that analyzes a log file, or a simple script that backs up an important folder. These little projects aren't just for practice, they're amazing portfolio pieces that tell an employer, hey, I know how to build real tools.
And that really brings us to the final, most important question. You now have the keys. You know how to make Python reach out and interact with the real world. So what are you going to do with it? What's the first tool that you are going to build?
All right, let's get into it. Today, we're going to tackle something that every single Python programmer runs into: how to master dates and times. Seriously, this is one of those skills you'll use all the time. Have you ever been there? You're just trying to figure out how many days are left until a deadline, or maybe you need to format a timestamp for a report and it just turns into this messy headache. It feels like it should be simple, right? Well, the good news is it actually is, because Python has the perfect tool for the job. And the whole secret really comes down to understanding one of Python's most powerful ideas, modules. The best way to think about them, they're like these pre-packed, specialized toolboxes ready for you to use. So yeah, a module is literally just a file packed with code that someone else already wrote and tested. So instead of you having to figure out the complex math for a square root, you just grab the math toolbox. And when you need to handle time, you just grab the datetime toolbox. It's all about working smarter, not harder. So let's go ahead and crack open that datetime toolbox. When you look inside, you're not just going to find one tool. You'll find a whole family of them, or as they're called in Python, classes. And each one has a very specific job to do.
Now, you'll find you keep coming back to 3 main tools. First, there's date, which is super simple. It's just for the year, month, and day. Perfect for birthdays. Then you've got datetime, the whole shebang. Date and time, right down to the microsecond. And finally, my favorite, timedelta. This is your magic wand for doing math with time.
Okay, that's enough theory. Let's get our hands dirty and actually put these tools to work. You'll see just how intuitive this all is once you start writing the code. So you need to know what today's date is. Check this out. First, you tell Python, hey, from that datetime toolbox, I need the date tool. Then you just ask that tool, what is today? And boom, you get this clean, simple, and super useful date object. But what if you need more than just the date? What if you need the exact time right now? Well, you just switch to a different tool. You grab the datetime tool instead of the date tool, and you ask it for now. And there you go, everything you need with incredible precision. Now, this is where the magic really happens. That output we just saw, it's not just a piece of text. It's a smart object. That means you can ask it for its individual parts. You can just say, hey, what year is it? Or what's the hour? Just by using a dot. It's incredibly powerful. Okay, so this brings us to a really important skill. We need to be able to translate between how the computer understands time and how we humans actually want to read it on a screen. You're gonna want to remember these two. strftim, and I want you to think F for format, takes that smart object and turns it into a pretty string for people to read. Then there's strpim, think P for parse, which does the exact opposite. It takes a string of text and turns it back into a smart object that you can actually do work with. So let's see that formatting in action. You see those little %sign codes? You're basically giving Python a recipe for how you want the date to look. Here, we're saying give me the full weekday name, then the day, then the full month name, and finally, the 4-digit year. And look at that beautiful output. Now, these codes, they're kind of like a secret language for formatting time. Don't worry, you absolutely do not need to memorize all of them. Just knowing these common ones here, like %y for year and %day for day, will get you 90% of the way there. Think of this table as your go-to cheat sheet.
And now, this is where we level up. This is where it gets really, really cool. We're going to move beyond just displaying time and start actually calculating with it. We're about to become time travelers, at least in our code.
And remember that third tool I mentioned, delta time? This is its time to shine. A delta time isn't a specific point in time, it's a duration. It represents an amount of time, like 10 days from now or 2 hours and 30 minutes ago. And look how beautifully simple this makes things. It's just 3 steps. 1, you get your starting point, today. 2, you define your journey, in this case, a time delta of 10 days. And 3, you just add them together to find your destination. It's so clean, so readable, it just makes sense. Okay, we've covered a lot of ground, so let's boil it all down. What are the absolute most important rules you should live by when you're working with dates and times in your code? If you take only one thing away from this, please let it be this. Always do your calculations and your logic with those smart datetime objects, never with plain strings. The second you get a date from a user or a file as text, use strip type to convert it into an object right away. Do all your math with time delta, and only use strip time at the very, very end, right before you show it to a person. Trust me, this habit will save you from so many future headaches. Think about it. By getting a handle on this one single module, you've just unlocked the power to build anything from a countdown timer to a project management tool to a complex event scheduling app. The logic of time is no longer a mystery. So the only question left is, what are you going to build?
Hey everyone, and welcome. Today, we're going to crack open one of Python's most powerful and honestly most fun built-in toolboxes, the random module. Let's jump right in.
You ever stop and think about what's really happening when you hit the shuffle button on your music app? Or how a video game can pull off a fair dice roll over and over again? Well, the secret sauce behind all of that is randomness, and lucky for us, Python gives us the exact tools to harness it.
But before we can start generating anything random, we got to talk about one of Python's secret weapons, modules. Just think of them as these prepackaged toolkits that save us from having to reinvent the wheel every time we start a new project.
So, what is a module really? At its heart, it's just a file packed with Python code. You know, functions, classes, all that good stuff. When you import a module, you get to use all of those tools instantly without writing them from scratch. It's seriously the best way to keep your code clean and super efficient.
Now, Python comes loaded with a bunch of these built-in toolboxes, and today we're grabbing the one labeled random. This one is incredibly versatile, as you're about to see.
Okay, here is the first thing you absolutely need to understand. Python's random module isn't, well, truly random. It's what we call pseudo-random. The numbers look random, but they're actually created by a predictable algorithm. The cool part is, we can control the starting point of that algorithm with something called a seed. See on the left? Without a seed, you get different numbers every single time. But look at the right. When you give it a seed, like we did with random.seed42, you get the exact same sequence of random numbers every single run. This is a game changer for testing your code because it makes your results reproducible.
All right, let's get our hands dirty and look at the first set of tools in our module. These are the real workhorses for just generating all sorts of random numbers.
First up, the most basic function of them all, random.randomparen. You don't give it any arguments, and it just hands you back a random float. That's a number with a decimal point, somewhere between 0 and 1. Super simple, super useful.
But what if you need a decimal that's, not between 0 and 1? No problem. That's what random.uniform is for. You give it a starting number and an ending number, and it'll spit out a random float anywhere in that custom range. And, of course, we need whole numbers. For that, we have random.randint.
This is your go-to for simulating things like a dice roll. You tell it the lowest and highest number you want, and it gives you a random integer in that range. And importantly, it includes both of those end numbers.
Generating numbers is awesome, but a lot of the time you need to make choices from a list of things. The random module has some really powerful tools for exactly that.
The simplest tool here is random.choice. You just hand it a list, or any sequence really, and it plucks out one single random item. It's perfect for things like picking a random winner from a list of names.
Okay, but what if you need to pick more than one item? This is where you have to pay attention, because there's a huge difference. Random.choices picks with replacement. Think of it like drawing a card from a deck, looking at it, and then putting it back in. You could easily draw the same card again. On the other hand, random.sample picks without replacement. Once an item is picked, it's gone. This is like dealing a hand for poker. Every card you get is unique.
And of course, what's a randomness toolbox without a shuffle button? The random.shuffle function is as straightforward as it gets. You give it a list, and it completely scrambles the order of the items. Just a quick heads up, it modifies the original list directly. We call that shuffling in place.
So we've seen all the individual tools. Now for the fun part. Let's see how we can put them together to build some genuinely useful stuff.
First up, let's do a classic. We're going to use what we've learned to build a super fast prize draw application. Who's going to be the lucky winner? Let's find out. And I mean, look how simple this is. We just make a list of our participants, Alice, Bob, Charlie. Then we use our new friend, random.choice, to just pick one name out of that hat. That's it. In basically 2 lines of code, we have a fair and random winner. So easy.
Let's step it up a notch and think about a password generator. The recipe is actually a perfect mix of what we just learned. First, you make a giant string or list of all the characters you want to allow. Then you just loop for however long you want the password to be, and in each loop, you use random.choice to grab one character. Finally, you just join all those random characters together into your new password.
We've covered a lot of ground, so let's quickly recap the most important bits. And then I've got one extremely important warning before we wrap this up.
Here it is, your cheat sheet. If you need a random integer, grab randent. For a float, use uniform. For picking just one thing, choice is your best friend. For picking several unique things, you want sample. To mix up a list, shuffle it. And remember, if you ever need your random results to be the same every time for testing, use seed.
And now for the big one. This is without a doubt the most important thing to remember from this whole explainer. Because the random module is predictable by design, it is absolutely, positively not secure enough for anything related to cryptography or security. Never, ever use it for real passwords or security tokens. For those mission-critical jobs, Python gives us a separate, much safer toolbox called the Secrets module. Use that instead. So there you have it. The whole toolbox is laid out for you. You can simulate, you can choose, you can shuffle. The possibilities are endless. So the only question left is, what unpredictable thing are you going to build first?